Hello, 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 everybody. Root Beer here. And we're going to be starting to take a look at Part B on the 2015 Canadian Open Math Contest. Okay, so Part B, questions worth a little bit more. So hopefully we'll give them a little bit more attention. But a quick reminder, we do just still need the final answer. It's Part C where everything must be written and justified. But these questions might be a little harder, so we might want to write some things down for part marks just in case we have missed our calculation, or we have missed a concept, or heck, we just can't finish the question. That's always a possibility. Alright, so B1, given an integer greater than or equal to 2, let f of n be the second largest positive divisor of n. That's kind of interesting. So obviously n divides n, but what's the next one? So for example, f of 12 is 6, because if we look at the divisors of 12, and we list them out in order, 6 is the next largest. And f13 would be 1. So as long as the number is not 1, it'll always have at least 2 factors, because it's either composite or prime, and so f will always be defined there. That's kind of nifty. I've never seen this function used before. Determine the largest positive integer n such that fn is 35. Okay, so 35. Well, can we find any other number, any number at all where fn is 35? Well, looking at the example of 6 here, why is 6 the biggest, and how can we get 12 from 6? Well, if we just double it, shouldn't it work? So f70, for example, should have factors 1, 2, 5, 10. Oops, I missed 7. 5, 7, 10. 14, 35, 70. So that one certainly works. Okay. Could we do more? What if I did something like, well, actually, it's probably important to note that n is equal to fn times some other factor. Okay? It has to be. Fn can't be equal to n. But fn is definitely a factor of n, so it's got to be, n has to be something times that fn. I think it has to even be a prime. Because what if I did something like 35 times 4? Well, then 35 times 2, which is 70, is still a factor of this number. This is incidentally 140. 70 is a greater factor than 35. Okay, so I think it's got to be a prime. Because if it were a composite number, with a not equal to 1 and b not equal to 1, then fn times a it's less than fn times, fn times a is greater than fn. So this is a contradiction, as we say. How could fn times a be bigger if fn is supposed to be the biggest one? So yeah, I guess it does have to be a prime. And that kind of narrows down the search a little bit. So that's why 2 works, 3 would work, I think. 5, 7. But of course, there isn't a biggest prime, so there has to be sort of some stopping of this. Okay. What could we have? Well, I know 35 is 5 times 7. So, and 2 worked fine, so maybe primes less than these will work. But what if I did something like n is 5 times 7 times 11? Because then 77 is a bigger factor than 35. Right? So that won't work. what if I did something like 5 times 7 times, well, what's the next lowest prime below 7? Below 11? It's 7, but now 49 will work. So that would be a bigger factor than 35, and it still isn't equal to the number n itself. So what if we tried just 5? Well, then we've also got 35 here, so that's fine. 35 here, and then 25. Yeah, this is it. Okay, and we could even write this number out and check it. 25 times 7, well, 25 times 4 is 100, so, you know, n equals 175 should do the trick. It has factors 1, 5, 7, 25, 35, and 175, so yeah, this works. And we just need our final answer, so there it is. Although I'm intrigued by this function, so I'm going to mess around with it, I think, ever so slightly more. So, you know, if you're just here for the answer to the question, 175, there it is. I'll see you for B2 in the next video. But I want to play around with this a little bit more because I think we might be able to, and, you know, this is part of what makes me a recreational mathematician, is I see this, I like it, I want to do more with it. I want to discover more of it. I want to put my own stamp on it, my own understanding on it. So I'm just going to play around with it just a little bit more. Not every question strikes my fancy, but I like a question like this. So maybe something like, suppose m is p1 to the e1, p2 to the e2. I'm just basically going to prime factorize this, with each of the pi's being prime, each of the ei's an integer greater than 0, and let's say that p1 is less than p2 is less than pk. Okay. The largest, I think the largest n having fn be equal to m is, so based off of what we just learned, duplicating primes willy-nilly doesn't work. You can't have bigger primes, so that won't work. But I think if I duplicate the lowest prime, so n is equal to m times p1, this should be the largest such number. Okay? So what might we say to sort of prove that? In order to have fn equal m, we must have n is equal to m times a prime. Okay? That, you know, we already sort of talked briefly about that, why a composite number won't work. So the question is, what's the biggest prime that we could have? It's got to be n times some p. If n is equal to m times p, p a prime, and if p is greater than p1, then maybe call it m prime equal to p times p1 to the e1 minus 1 times p2 to the e2 pk to the ek is greater than m, and a non-trivial, that is to say not one of the obvious ones, not 1 or the number itself, so a non-trivial factor of n. So that wouldn't work. Then we wouldn't be looking specifically at fn. We'd have fn is at least m prime. So that wouldn't work. So, okay. If p is less than or equal to p1, then any factor of n that isn't n has well, let's say looks like, is either a factor of m or a non-trivial factor of m times r prime p. So obviously if it's a factor of m, then it's smaller than or equal. So these guys are less than or equal to m. M is the biggest amongst those. We just need to show that a non-trivial factor of m times p is also less than or equal to m. So that would look like p to the times 1 to the d1 times p2 to the d2 times pk to the ek, or sorry, dk, where each di is less than or equal to ei. And well, since I'm exploring this on my own, I'm just going to use a little summation notation. This is less than the sum of the original ei's. Then since p is less than or equal to p1, which is less than all the other primes, we get a larger factor of n by replacing p with pi, where di is, where I is such that, let's say where I is one of the indices with di actually less than ei. If each of the di's is less than or equal to ei and the sum is strictly less than the ei, then at least one of these must be true. So this is a factor of m, and so m really is the biggest thing. And there we go. We've sort of generalized the problem. So the largest n having fn equal to m really is m times the smallest prime that appears in the prime factorization of m. Cool. I like that. I like that. I like the question. I like the concept. I liked my generalization. You might have a different way of going about it, but I really like that. It's fun when a math question sort of stays in your brain after you're done looking at it. Anyway, all that set aside, we're going to be looking at B2 in the next video. You are more than welcome to join me there, and I will see you for more math in the next video. Take care.